viewers, welcome back to our channel and Vinay Kumar Basics of Physics. Dear friends, in this video we are going to discuss about the p-type semiconductors. What are the p-type semiconductors? So children, in the previous video we discussed about the intrinsic semiconductors. Now we can go for the extrinsic semiconductors. Extrinsic semiconductors. So extrinsic semiconductors, how they can form when some impurities are added to the pure semiconductors, then extrinsic semiconductors are formed when certain amount of impurities like trivalent and pentavalent impurities are added to the pure semiconductors, then extrinsic semiconductors are formed. And in this case children, there is one 2 marks question is there, very important. What is mean by doping? Doping is nothing but process of adding of impurities to the pure semiconductors to increase the conductivity. That should be what we call doping. What is doping? Process of adding impurities to the pure semiconductors. Process of adding impurities to the pure semiconductors is called doping. Clear? So already we know germanium and silicon are the best example for pure semiconductors. Here pure semiconductors means nothing but intrinsic semiconductors. For that, if you can add the impurities means valence electrons. When we are adding the valence electrons, then the conductivity is increased. Already we discussed in case of intrinsic semiconductors, there are some atoms are there. Every atom can forms the 4 covalent bonds with the surrounding atoms. So we clearly discussed in the previous video why the conductivity is very less for intrinsic semiconductors. In any intrinsic semiconductor, the atom has only 4 valence electrons. These 4 valence electrons forms the covalent bond with the surrounding 4 atoms. That's why there are no valence electrons at a 0 Kelvin temperature. When we increase some temperature, then only some conductivity is going to be increased. So I clearly explained about the intrinsic semiconductors in the previous video. I will provide the link of that particular video. You have to watch it. So here children, germanium and silicon must be taken as the intrinsic semiconductors or pure semiconductors. For that, impurities are added. Impurities nothing but what it is? Free valence electron. Free or valence electron should be added. So here for pure semiconductors, if trivalent impurities are added, then that is what we call p-type semiconductor is found. And for pure semiconductors, if we can add pentavalent impurities, then n-type semiconductor is formed. Here p-type and n-type should be called as the extrinsic semiconductors. Clear children? What is the here p-type semiconductor? When trivalent impurity atom should be added to the pure semiconductor, then p-type semiconductor can be formed. When pentavalent impurity atoms are added to the pure semiconductors, then n-type semiconductors are formed. Clear children? Extrinsic semiconductors are formed because of the process of doping. These extrinsic semiconductors can be classified into two types. p-type semiconductors and n-type semiconductors. Now we clearly discuss about the p-type semiconductors in this particular video. So just now only we discussed, children, when and how we will get the p-type semiconductor. P-type semiconductor, when it is formed, when trivalent impurities can be added to the pure semiconductors, then p-type semiconductor formed. Let's see how the conductivity is in the p-type semiconductors. Look here. So germanium or silicon, they can be taken as intrinsic semiconductors. They have 4 valence electrons. 4 valence electrons are there. Clear? For that we have to add the trivalent impurities. So that means what? We have to add the 3 valence electrons atom to the germanium or silicon. Here we will take boron and aluminum are the trivalent atom. Then what's happened? Look here now. So this is the one trivalent. What I am going to say here, simply we are going to take some aluminum, and that should be surrounded by the like so many silicon atoms like this. Clear? So here aluminum has how many valence electrons? So just now we discussed, that is the trivalent atom. That's why for aluminum how many valence are there? 3 there. And for silicon 4 valence. It is the trivalent atom. That's why here 4 plus 3 7. So if we can write 3 pairs and one additional electron is there. Look here now. So I am showing this is the one valence electron, and this is the second one, and this is the third one. For aluminum, this is the first valence, second valence, and third valence. Clear? And now we can go for silicon atoms. They have 4 valence electrons. 4 valence electrons. Let's see what happened here, children. So very simple to understand. Here this is the silicon. Thus we having 4 valence electrons. 4 valence electron. So this is the one electron. And again next one. This is another silicon. Thus we having 4 valence electrons like this. Okay. And this is the one more silicon. Thus we having some 4 valence electrons. And this is the another one. One is like this. So for every silicon there are 4 valence electrons are there. That's why here you have to understand this aluminum and this one silicon can form this is the first covalent bond. It means that what? Aluminum can form the 3 covalent bonds with the 3 surrounding silicon atoms. Here there is one particular only one electron is there. Here one more electron is there to form the another covalent bond. So actually here 4 plus 3 7 electrons are there. If they want to 4 covalent bonds, it required one electron. Like that. Here the central, or this is what we call, this aluminum is called as the dopant atom. What it is? Dopant atom. So that dopant atom has 3 valence electrons. That atom will form the 3 covalent bonds only with the surrounding silicon or germanium atoms. Clear? So that particular dopant atom is required one more electron to form the another bond. So here there is one electron is required. Lack of electron is there. That should be called here hole. Already children, hole is there. Very simple to understand. In case of p-type semiconductors, there is one dopant atom. It is there. Dopant atom is nothing but trivalent impurity atom that can form the 3 covalent bonds with the surrounding atoms, and one more electron is required to form the 4th covalent bond. This required electron should be nothing but what it is? Deficiency of electron. What it is? Deficiency of electron. The deficiency of electron is called hole. Clear? So this is the first thing you have to remember. This is the what it is? Hole. After that, You have to observe here this hole is must be again filled by the atom of the surrounding silicon atoms. Clear? So what we discussed up to now, one electron is required to form the fourth covalent bond. The deficiency of electron is what we call hole. It is very clear. So that hole must be filled by the remaining any one of these silicon atoms. That means what? For example, this electron wants to go here. Then obviously what happened here? Here hole is formed. Again this hole must be again refilled by the another electron of another atom. Like that, what you have to say? So many holes are created. So many holes are created. When this dopant atom is ready to take the electron, that is what we call here acceptor atom. Acceptor atom. So here now, what you understand here? First hole is created. Why? Because there is some electron is there. It's very clear. So the surrounding silicon atom will give the electron. Then automatically this hole is refilled. That's why here what I am to say, this dopant atom is always tries to receive the electrons. Receive the electron. That's why it is called as the acceptor atom or acceptor ion. That's why here what I have to say, in p-type semiconductors, so many holes are formed. Here first hole it is there and that should be refilled by the electron which is here. Then hole it is formed. Again this hole must be filled by the another electron. Then hole is created here. Again this hole must be filled by the another electron, like that. That's why here what I have to say, so many holes are created. So many holes are created. That's why in p-type semiconductors, holes are the majority. Holes are the majority charge carriers. Majority charge carriers, and electrons are the minor charge carriers. Minor charge carriers. That's you have to remember. In p-type, holes are the majority and electrons are the minority. That's why here we will write NH is greater than Ne. What is? NH is greater than Ne. What is NH? Number of holes is greater than the number of electrons. That's why NH is what we call majority carriers and Ne is what we call minor. So children, in this case here we have to remember, in case of p-type semiconductors, if you can go for the energy bands, so it is the now what I have to say, valency band, and this is the energy gap, and this is the conduction band. This is what? Conduction energy of the conduction band, and this is the energy of valency band. And here the Fermi energy level is close to the valency band because holes are created in the valency band only. That's why what you have to say here, in this case, in case of p-type material or p-type semiconductor, what you have to say, the Fermi energy level is close to the what it is, valence band. And now children, the conductivity should be given by the formula. So conductivity is equals to NH into mu into E. Here sigma is the conductivity and mu is the mobility and NH is the number of holes and E is the electrons. So that is the expression for conductivity of p-type material. So children, I hope you understand. If you can understand this one, like, share, comment the video and subscribe our channel to get all notifications. And my request is suggest my channel to your friends also. Okay, thank you for watching.